Hey, hi everyone. I'm Diana Zigterman. I work at Google on our Chromebooks. I'm on the embedded controller team, and specifically I'm our USB-C lead on the embedded controller team. So today, naturally, I'm here to talk to you about USB-C. So the first thing we're going to go over is the Type-C specification, just a brief overview of what it does, what it entails for connections. Then we're going to add USB power delivery on top of that. And then we're going to go over our USB-C stack plans we have for Zephyr. So first up is our friend, the USB Type-C specification. So the specification is available on usb.org. As with most of these specifications, there's a lot of jargon involved. So at the beginning of every section, I just put together a quick little vocabulary list to go through before we dive into the concepts that go with the section. So for this one, we've got a sink. A sink is going to be your port partner consuming power. So your phone, when it's charging, is being a sink. USB sticks are pretty much always sinks. And then we've got sources. Sources are going to be the port partner supplying power. So your wall charger is always a source. If your laptop's connected to a simple hub, your laptop is acting as a source for that connection. And then we also have dual rule ports. So those are partners that can be sources or sinks. So a laptop or a phone or a dock are usually the prime examples of this, where they can either source or sync, and they have to make policy decisions based on how their connection is going to figure out which one of those is appropriate. And then we've got VBus. So VBus is going to be the voltage provided from the source to the sink to power the sink. That can range anywhere from 5 volts all the way up to 48 volts at this point. And then we also have a VCon, which will be very similarly named, but totally different. VCon will be an optional voltage you can provide to a powered cable. And you can think of it as a connection voltage to kind of help you keep it separate from VBus in your mind. So first thing we're going to do is going to get to know your Type-C receptacle. So as you can see, it's got 24 pins. We'll start from the middle. In the middle, we have D plus and D minus. This is providing us USB 2.0 functionality. And you'll notice there are 2 sets of them. This is how USB-C is flippable. We've got duplicates of all the pins. And on the host side, the host needs to detect the polarity of the connection and arrange its muxes and retimers and stuff accordingly in order to make that connection work. So rather than making the user sit there trying to plug things in the right way, we just try and make it so both orientations always work by having these redundant pins. Up next to the D plus D minus, we have the CC lines. These are the configuration channels. We're going to dive into these a lot more for the Type-C connections and for the power delivery connections because they're essential for how those work. Next, then we have the SBU lines. These lines are available for use for DisplayPort aux signaling. They're also used for USB 4 mode. And if you attended Keith's talk about Chrome OS embedded controllers, you'll notice he mentioned we had a debug accessory we could just plug into the Type-C ports. These lines are what we use to send consoles over our debug accessory. Up next, we've got VBus. So this is that voltage we talked about that can range from 5 volts to 48 volts. That's delivering power through to the sink. And last but not least, we've got our USB 3.2 super speeds pairs, and then these are also used in USB 4. So your host side is going to have all these pins present. It's going to mux them appropriately. Your device side will have whatever pins it needs present. So for example, if you were a USB 2.0 device of some sort, all you'd need to connect is D plus, D minus, CC, VBus ground, and you don't need to connect any of the rest of the pins. So what does it look like when we actually do a plugin? So if you're a source, you are going to have a pull up on the CC line called RP. The specific value and strength of RP is actually going to be your method of advertising your power supply to any sinks that connect. So you can advertise that you only do default USB power, 1.5 amps or 3 amps. So you can get up to 15 watts on a Type-C connection just through this advertisement of the resistor value alone at the beginning of the connection. And then on the sink side, the sink is going to be presenting RD on both of its pins. And if you'll notice in this diagram, usually cables only connect through one of the CC lines. This is how you detect your polarity on the connection. So one of the CC lines will connect RP through to RD. The other CC line may be attached to something called RA. This is something that electronically marked cables will have, and that's where you apply VCon to electronically marked cables in order to power those cables. And then if you're a dual rule device, so if you can supply power or consume power, you actually sit there and you toggle back and forth between RP as a pull up and RD as a pull down in order to be able to make connections with both of these types of devices. So what does that actually look like on the voltage lines? This is just a quick capture off of my PD analyzer, but basically we've got This is our dual roll ports CC line. It's altering between presenting that RP pull up or the RD pull down in order to make a connection. And then at some point while we were presenting RD, a sink attached. So now when we try and go back up to RP, we actually find our voltage is lower because we now have an RD attached through the other side. And if you're wondering, this RP strength indicates that we can supply them 1.5 amps on the beginning of the connection. So this is a 7.5 watt connection. So once we get those CC voltages to bounced, we're going to enter our attach state. We're either going to be attached.source or attached.sink. If we're attached.source, it's our duty to provide 5 volts on VBus. We may provide 5 volts on VCon. The applicability of VCon depends on a complex table in the Type-C spec if you're ever curious enough to look it up. But that 5 volts of VCon would be on that RA pin, the one that doesn't connect through the cable. And then the source is going to monitor the CC lines to know when the sink detaches, and it needs to make sure that it discharges VBus after sink detach, because obviously you don't want to just leave VBus hot on your cable. The sink side is going to begin consuming power, and it can consume up to its RP advertised current. So up to potentially as much as 15 watts if that's what the source is advertised on its RP. And then the sink's job is going to be to monitor VBus to know the source is detached. It can optionally also monitor the CC lines, but VBus is the one that the specification has called out as being required to monitor for source detach. And so once we're in attached source and attached sink, we have port roles. We've got 3 roles that each port partner has. There's the power role, so who's supplying VBus, you're either the source or the sink. Data role, so that's who the host is of the connection. You're either the DFP or the UFP, and we'll get into those acronyms in the next section. And you've got a VCon role, so you're either the VCon supplier or you're not the VCon supplier. So if you don't have power delivery support, these roles are going to be fixed for the entire lifetime of the connection. So if you have a non-PD charger, that non-PD charger will always be source, DFP, VCon source. If you've got a USB flash drive plugged in, that flash drive will always be sync UFP, not VCon source, for the full duration of the connection. But if you have power delivery, we can delve into the power delivery specification. So this is a separate specification from Type-C, also available on USB.org. And everything in this specification is what happens after the Type-C layer has gotten to that attached.source or attached.sink state. So for this section, obviously we have PD, which is power delivery. So it's that specification that's providing our messaging on these connections to allow us to have a much larger feature set of things we can do beyond just delivering 15 watts of power. We've got DFPs. So these are the port that are the USB host root port or hub downstream port. So your laptop, it's always going to be a DFP, pretty much always. If you're thinking about a dock, dock's connections to its flash drives or monitors are going to be, it's going to be DFP on those connections. And then they've got the UFP, which is the other data role. It's the data role of the USB device. So a monitor will be a UFP, a flash drive will be a UFP. If you think about a dock connecting through to your laptop, the dock will be a DFP to its flash drives and monitors, but it will be a UFP to your laptop. So how do these PD messages come through? They actually get sent on that CC line, the one which is connecting RP through to RD that we use to detect polarity after plug-in. So the layer responsible for the actual signaling itself is the PHY, the physical layer. It's in chapter 5 of the PD spec if you're deeply curious about it. But basically it's going to encode data, it's going to transmit it, it's going to have special symbols to indicate things like start of packet, end of packet, reset sequences, those kinds of things. And you'll have PD messages going across the line using this encoding in the PHY layer. The PD messages can just be commands. Those are called control messages. They don't have any data attached to them. Or they can be data messages, which do have extra bytes to indicate more data. Nowadays, we also have extended messages, which are data messages that are just extra big. And if you're curious about the variety of messages they're in chapter 6 of the PD specification. So let's start with contract negotiation. So every single power delivery connection has to start with an explicit contract negotiation. So once you've plugged in, once you're in attached.source and attached.sink, the source port's job is going to be to send source capabilities. It'll send this as a data message, and the data message indicates like, hey, these are all of the voltages I have to offer. Also some additional little tidbits about myself, like whether it supports USB communication, whether it has unconstrained power, i.e. it's like plugged into a wall. And it'll keep sending these out for 5 to 10 seconds until the sink port's ready. because the sync port may take a while to become ready if it was just powered on by the presence of VBus. So once the sync port is ready, it's lucid, it's ready to communicate, it is going to send a good CRC. So the good CRC is a special control message we use to indicate that the previous message was received and it checked out correctly, and we're good to go for communications. So these are used constantly. They're used in response to every single PD message. So after this, I'll just illustrate them as arrows, but just know that good CRCs are always there or should always be there, and if they're not, it's a problem. So the sync port says good CRC. That tells the source port that it's connected to a PD-capable partner of some sort. And the sync port now needs to contemplate what it wants from the source capabilities. So it looks through that menu of voltages and currents available. It says, okay, I would like to select this one, sends it to the source port. Source port's going to good CRC, of course. And then the source port will accept. It'll say, okay, this seems reasonable. I'm going to provide you your power. And once it's got everything turned on, the rails are all ready, it's going to send a power supply message, ready message. This is a control message that marks the end of the explicit contract negotiation. So as soon as that power supply ready message is sent, both partners enter into a ready state where they can send or receive any kind of PD message. So what can we do with these PD messages? There's a lot of them at this point. We can negotiate PD contracts. We can get up to 240 watts on them now as of the PD 3.1 specification that came out very recently. We can swap around any roles. So all of those roles we talked about earlier, Power, Data, VCon, they're all up for swaps if people want to swap. You can gather information about electronically marked cables. So for example, you can probe a cable you're attached to ask whether it can run 5 amps on it or not in order to get up to higher power levels. You can enter into alternate modes. So you can enter DisplayPort, Thunderbolt mode, USB 4, all of those come through PD messages. You can probe manufacturer information. You can actually ask your port partner, like, hey, what is your vendor and product ID? What are you doing? And then as part of that, you can also probe whether it supports DisplayPort or supports Thunderbolt, those kind of things. You can retrieve battery information. And then PD also has built-in methods of recovering from errors. So we've got soft resets for if there's a protocol error, so if someone misses their good CRC. And they have hard resets for larger communication errors that happen on the system. So we've got several different layers of error recovery built in to the protocol. So if we zoom in on our roles from earlier, we're going to have extended responsibilities and also privileges that come with our roles now. So the source is going to be still going to be the one supplying power, but it also has to control collision avoidance as of PD 3.0. As you can imagine, with that one line going through, it's very feasible that 2 messages can collide on the wire and neither one of them gets through. So as of PD 3.0, we introduced collision avoidance, where the source side is going to use its RP values to now indicate whether the sync can transmit a message or not to prevent those collisions. For data role, the DFP is the one who is allowed to decide alternate mode entries. So your laptop gets to decide whether we enter DisplayPort mode, not the monitor that you are attached to. It's all up to your laptop where and when it wants to implement alternate modes. In PD 2.0, it also was the only one allowed to gather partner information, but it changed that in 3.0 to be more flexible. And then VCon role. So the VCon supplier is the one who also has the privilege of getting to talk to the cable. The cable has its own special startup packets to talk to it. Only one port partner can obviously do that at a time without confusing things. So the VCon supplier is the one who's allowed to talk to the cable. And you might need to do this if you need to assess whether you need higher power. You especially need to do this if you're trying to support something like Thunderbolt or USB 4, which have a lot of very specific cable requirements that come with them. So that's kind of a brief overview of all of the roles in PD, the kinds of messages you can send. And from there, we're going to dive into our Zephyr USB-C subsystem overview. So if you catch Sam's presentation, he's going to get more into the code, the pull requests involved for the code, and what it looks like to run it. I'm going to be more on the block diagram side of what it looks like. So for this section, our new jargon is DPM. We have a device policy manager, and this is the application code that makes the higher level decisions about what we want to have happen on the USB-C connection. Because as you can guess from how many PD messages there are, there's a lot of things you can do. And so the device policy manager is going to be the one guiding what it is we do there. TCPM is the Type-C port manager, and that's going to be managing the state of the USB-C connection. So it's going to be packaging up those messages, sending them, doing error checking, running all the protocol checks and things like that. And in our case, this is going to be running as a thread in Zephyr for the subsystem. A TCPC is a Type-C port controller, and that's going to be controlling the physical communication on the CC line. So it's going to be in charge of setting CC terminations, reporting what the CC voltages are, sending and receiving PD messages, doing all of that PHY layer encoding kind of stuff, and generating good CRCs. So starting out with the subsystem thread itself, we've got 3 layers. We're going to start at the bottom layer of the subsystem thread. We have the Type-C state machine. This is going to handle all those things from our first section of the presentation. So it's going to handle the CC line connection, VBus connection, and then monitor for disconnection. 1 layer above it, we've got the protocol layer. You can kind of think of this as like the post office of the stack. It's going to be composing the PD messages, putting message IDs on them, getting ready to send, getting them received, deduplicating any duplicate messages from the port partner. And then above it, we've got the policy engine. And the policy engine is the one who knows how to put messages together, knows what appropriate responses are to different messages, those types of things. And it can detect protocol errors in terms of unexpected messages. So the first layer, the Type-C layer, is actually directly from the Type-C specification. It's a set of state diagrams you can find in the configuration channel section of the Type-C specification. And same with the PRL and PE layers. They're both directly pulled from the USB PD specification. So for all of these, the states, their state transitions are directly defined in the specification. So if you come across a problem where you're like, hey, what is try-wait sync doing? Or what is PE sync startup doing? You can actually directly pull up the specification and compare what it describes the state is doing and what it describes the proper transitions as being compared to what the code is doing and what you see. So then on top of these, we need a device policy manager. So this is also defined in the Power Delivery Specification, but it's not a set of concrete states or anything. It's just a set of responsibilities. So the DPM needs to be responsible for selecting voltages to offer, voltages to consume. It needs to manage any shared power concerns. So if you have one pool of power from which you can give power to several ports, it needs to manage the allocation of power over those ports. It needs to indicate when power supply transitions are complete, so it lets the PE know when it's ready for VBus to be sourced. It also needs to be the one to ask for extra information from the port partners if it needs to know more information about cables or about the connected partner. And it's going to be the one that detects and selects the alternate modes. So if anything's going to decide we're doing Thunderbolt or DisplayPort or USB 4, it's the device policy manager who's going to make that call. And then, so if we kind of imagine these both together, we have on the left the column representing the USB-C thread. So that's the subsystem thread with the layers we talked about earlier. And then on the right's the application code for the DPM. So you see we've got what our TC layer, our PRL layer, and our PE layer. And both the PE and the TC are going to have callbacks into the DPM. So anytime they run into something where we're not sure what the policy should be, you call back into the DPM to ask like, hey, what is it we'd like to be doing right now? Are we presenting RP? Are we presenting RD? Are we toggling? And from the PE layer, asking things like what voltage or is it appropriate for us to ask for right now or to provide right now? And then similarly, the DPM has requests it can make of those layers. It could ask the TC layer to suspend the port to set its CC lines to open because we don't want to connect to anything right now. It can ask the PE layer to send certain control messages, to request certain data messages. And so that's kind of how they interact together and how they're siloed. And then if we look down to the diagram to the bottom left, you'll see a TCPC driver. So the TCPC driver is where the TC is going to reference to get the CC line set to get what the voltage are on, what the voltage is on them. It's also going to be the thing that the PRL talks to receive messages, to send messages, to enable good CRC generation. And so we're going to dive into those a little bit more. So why are there TCPCs here? So in our implementation for Chromebooks especially, we find it very helpful to have a specific separate chip performing all of the PHY layer operations. So it's performing all of the encodings, the noise detection, and TCPCs themselves will offer you a very flexible API such that you're still determining the overall messages and the overall connection scheme and what's happening, but at the same time taking all of the base PHY layer stuff off of your plate so you don't have to deal with it. Especially, so some PD interactions like the good CRC generation have to take place on a tight time scale. So I believe good CRC needs to be sent within 1 millisecond of the message that it's replying to. And if you are running on an embedded controller that has other things to do, if you're running keyboard scanning as well as sensors, as well as temperature checks and things like that, you might not be able to reply in that 1 millisecond. And so the TCPC can reply for you. You can get TCPCs embedded into ECs. I've seen ones embedded that will automatically generate good CRCs for you. I've seen one or two embedded that need a high priority task to actually generate the good CRC. So a register will tell you that the CRC checked out, but you still have to compose the good CRC and send it yourself. And then you can also have external TCPCs. So these actually have, again, their own specification on USB.org. In this case, the Type-C Port Controller Interface Specification, or TCPCI. TCPCI defines a set of registers you need for base functionality. Then it also has registers which can be optional features for chips to implement. And then it also has a vendor-defined specification, region of registers available for vendors if they need to customize things. So what TCPCI provides us is that anytime you have a chip that complies to TCPCI, you have very few chip-specific driver functionalities needed. You can mostly just use a generic TCPCI driver. Some of the vendor-specific things you might need would include, like, we have one TCPC that needs a special sequence to be sent to it before it'll unlock, allowing you to send I2C to the TCPC. Usually small things like that. So the additional feature sets that you can have that can include VBus ADCs, VBus discharge, overcurrent protection, VCON sourcing, VBus sourcing, and these will all be they're features that'll have a configuration register that indicate if the feature is present, and when it is, you can just use the TCPCI defined registers to access that feature. And then some external TCPC chips can also just integrate other functionalities that are really useful. We've got TCPC chips that include battery charging capability. So if you've got one Type-C port and a battery, you can have that TCPC also manage charging the battery. We've got ones that include USB line muxing and retimers, and I believe we're getting one very soon that includes SBU fault protection. So they can offer you a lot of extra functionality while still giving you a very good amount of flexibility on your connection, so it's not dictating how your connection is run. And we find those to be very useful, which is why they're the base of how our stack works. So let's get into what it looks like from the Zephyr application point of view. We're going to go back to that initial contract negotiation we went over, except now we're going to imagine the sync port is divided into a USB-C subsystem thread and an application layer. So the source is still going to send its source capabilities. We're still going to good CRC. That good CRC will be generated by the TCPC. The USB-C thread receives the source capabilities message, and it says, oh, hey, I'm going to tell the application I've got some source capabilities. The application can store these. It can use them to decide internal variable states. It can do nothing at all with them if it doesn't actually need them for any reason. And then the USB-C thread is going to ask, like, hey, what are we doing here? What should we be asking for? And the application layer will look through that menu of options, and it'll say, like, hey, I need this voltage, this current, put it together in a request data object. And then the USB-C thread will package that up. It'll add on the right message ID and everything and send it off to the source port. Everything else will pretty much continue as before, except at the very end, when we get our power system or a power supply ready message from the port partner, the USB-C thread will actually take that time to say, oh, hey, application, your power is ready. So then the application can respond by setting FETs if it needs to set FETs. It can set charging current limits if it needs to set current limits to ensure it doesn't overdraw on the port. Whatever it is it needs to do based on its new power, it can do that via the callback. And so an example of what happens if the application wants to start initiating its own sequence. The application can send a request in. In this case, the application is going to say, hey, you know what? I would like to be a DFP. They'll send that request into the USB-C thread. The USB-C thread will service it as soon as it's in a ready state. So as soon as we're not in the middle of like another power negotiation or any other kind of reset process or anything. And the USB-C thread will take that request and it'll compose a data role swap control message. So that message basically says, hey, I want the opposite data role of what I have right now. It'll send it off to the port partner, and the port partner is going to look at that, and it could send us a reject saying no. It could send us a wait saying, ask me again later. In this case, we're going to say it says accept. It says, sure, sounds good. Go ahead, be the DFP. I don't care. The USB-C thread will then notify the application layer that it was successful. And this callback, the application layer may need to do something like setting muxes or setting retimers to adjust to its new power role. And so again, if you want to know what the specific code looks like as opposed to the block diagram view, I'd recommend checking out Sam Hurst's talk. I also put together some additional resources of just links to all of the specifications I mentioned. I would recommend a good PDF viewer for them because they're very dense specifications, especially the PD one. Personally, I use Zephyr. It has Vim key bindings for searching the PDFs. It's very useful. And with that, we come to questions.
Thank you, Diane. There was a question on the Discord from Andy, but I think Andy then clarified later that you might have answered it. But just to be sure, it says, regarding the command framing, is the idea that the EC hardware is providing the hardware controller for the PD commands on the CC lines. Is it like I2C or like? Or some statements seem to imply that Zephyr driver is bit banging this. And then later he had a comment. I don't know if you want to confirm or deny that.
So the external TCPCs are pretty much always I2C. Usually you'll want to run them at least like 400 kilohertz to get a good response time out of your system. And then the internal TCPCs usually use just a specified set of registers. So if you're on like an STM chip or an ITE chip, there'll usually just be a set of registers you use to grab out your TCPC information.
Okay, thank you. Are there any questions in the room here? We got a question.
Hi, yeah, so this is really great work. I know when I've looked at this in the past, there's some, I think it's like a microchip IC that specifically you put it there right in front of your USB-C port, and it kind of deals with a lot of this for you. Is that kind of what you're talking about when you're talking about a TCPC? Yeah, it's really hard to keep track of all the acronyms, but.
So the TCPC, it pretty much just exists to deal with this PHY layer, the CC line layer. Whereas if you have, I think you might be describing a PD chip.
Yes.
Usually those are the ones that are going to make decisions for you. So they're usually good for simple USB-C applications, but it's harder to charge from USB-C, for example, with one of those chips because they're going to be the ones making your requests and you have to try and interface with them in order to get your requests through.
Okay, I think that makes sense.
Usually those use the UCSI specification.
That sounds right. Yeah, it's been a while. Thank you.
Any other questions? Here's one.
Given the complexity of what you just described, what level of stability do you see in the current shipping set of chips, chipsets, etc., when it comes to this, in terms of being able to establish and maintain proper connections, charging, as well as run various data protocols at the same time?
So I think what we see in our Chromebooks is most of the ecosystem is generally stable at this point. A lot of the major vendors especially will use, they'll go through PD compliance testing for their products. There's always going to be some random peripherals. I think I have just like a whole stack of just random peripherals where they overdraw VCON or they cause like VBus voltage spikes, or one VGA dongle that won't good CRC if you ask it about its source capabilities. So there are random corner cases, but if you make your code robust enough, usually you can at least recover from that using the PD mechanisms available.
Is there any other questions in this room? Got one on the front.
Hi, I'd just like to say that was a fantastic deep dive. So great job. And also, I'm curious to know if you were able to test out any controllers with the TCPC built-in that did actually require software intervention for the CRC, and if you're running Zephyr, and in that case, if you had managed to collect any jitter information.
So I'm not sure if we have jitter information. We have one Chrome dock codenamed Honeybuns, which uses an STM controller that needs to generate its own good CRCs, and that passed, I think, nearly all of its compliance suite until we ran into one hardware limitation regarding dead battery RDs. And then I believe Sam's demo is also on an STM board using the good CRC generation.
Do we have any other questions? Okay, well, thank you very much for your presentation. You get to wrap up all the presentations on this in this room for this session of ZDS, and so I thank you very much for presenting. And
Thank you.